it can be seen that the current through the coil increases as the voltage applied increases. For the voltages from 0 to 8 volts, the graph is a straight line passing through the origin. The resistance of the coil is constant at 2 ohms for currents up to 4 amps. The gradient of the voltage current graph is constant. At currents above this value, the coil starts to become hot. Vibration of metal ions within the wire increases, and the charged particles that make up the current find it more difficult to pass through. The resistance of the coil increases. This effect becomes more evident at 9 and 10 volts. As we have seen, the resistance is constant at 2 ohms, provided the temperature is constant. The experiment is now repeated with 2 further copper coils, B and C. A graph showing voltage applied to the lamp against current flowing is shown above. The gradient of the voltage current graph increases as the current through the filament increases. The resistance of the filament is therefore increasing. Larger currents cause the filament to become hotter, therefore increasing its resistance. A graph of current flowing through the diode against applied voltage is shown above. No current flows until the applied voltage exceeds 0.6 volts. The resistance of the diode up to 0.6 volts is very large. Beyond 0.6 volts, the resistance of the diode decreases and the current flowing increases rapidly. The diode has begun to conduct. The experiment has been repeated with a diode connected in reverse bias. As you can see, the diode will allow absolutely no current to flow in the circuit. We can say that the diode does not conduct when connected in reverse bias. The forward and reverse current voltage graphs have been combined and are shown above. Reverse bias voltages are shown as negative values. Diodes will only allow a current to flow in one direction around a circuit. They are used in rectifying circuits to convert alternating current into direct current.